lot of cool stuff to show today. He is the, I want to say the Stephen, he's Stephen Barna, Professor of Experimental Aerodynamics in the Department of Mechanical and Aerospace Engineering at Old Dominion University. And so I'll let you take the mic. So thank you.
There we go. Well, I was told to try to be entertaining, so I'm going to try to be entertaining, but we'll see how it goes. So we got into this area of work kind of by accident, a little bit, as you'll see, and it's turned out to be rather fascinating, and a surprising amount of related work has gone on over the years, which I'll touch on a little bit. But the basic phenomena is fairly well known. A 2D rectangular shape dropped appropriately will tumble end over end with sort of a backspin kind of trajectory. And a regular business card works. So I think I'm still visible if I drop it like this. That glides at about a 45-degree angle, which means the lift to drag ratio is roughly 1. And okay, academics have studied that experimentally and computationally and theoretically, and there's all kinds of papers talking about the physics behind it. There's 2 other modes of flight. I'll just start this video while I'm talking. There's 2 other modes where it's the falling. I've got sound that I don't. How do I stop the sound? I go mute somewhere. There. That one. Oh, this one. Okay.
So no questions.
We're back. Okay, I think that worked. So there's 2 other modes of motion. There's a falling leaf mode where it goes from side to side, and there's a chaotic mode where it can't decide which mode of descent to adopt, and that depends on the length to chord ratio. Now the video shows derivative of this idea, which is the tumble wing. You can take any little piece of paper and turn it into a wing which will fly at a better lift to drag ratio. And rather cutely, if you run behind it with a board inclined at an angle, you create enough upwash to zero out its descent rate. And so it'll basically go into cruise. And the video that was playing rather sporadically there, if you stop it at just the right place, the eagle-eyed among you might notice that this is the Air and Space Museum in Ottawa, which is very, very good. And one thing they have, which is very rare, you can see in the background there, is an Avro Lancaster. There's not many of those left in the world, but so if you're ever in Ottawa, go see it. So, okay, some background. It extends to regular aircraft, quote, regular aircraft, and the Northrop flying wings were apparently susceptible to this phenomena, and the YB-49 had an end-over-end tumble instability, which sounds really scary and was probably the reason for the crash, the fatal crash of the second prototype. There's some testimony there from one of the pilots, and it says, you know, as I entered my first stall, instead of a normal stall, it lurched forward and went into a full negative tumble, which I take to be nose down, kind of tail over nose rotation. And to get out of it, he used asymmetric thrust to convert the tumble into a sort of corkscrew mode and then into a regular spin, and then they could do spin recovery. Well, that's really scary. One of the recommendations was that this thing needs a flight control system. but of course that was before flight control systems were common. A lot of work was done to study the effect, including some computational work 20 odd years ago on a similar kind of planform. Case Van Dam, who he knows what he's doing, did some work, and it was compared to some spin tunnel tests here, Mike Fremo and others involved. A little bit inconclusive on the cause and the way to mitigate the effect, but the key discovery was, the key conclusion was static aerodynamic information was not sufficient to describe the motion. If you see the graph there, which is from the computational work, the static aerodynamic results over a full 360-degree rotation in pitch are roughly symmetric. So if you integrate pitching moment over a full cycle, you get roughly zero, which means nothing will happen. If you include the dynamic effects, damping, time delay of stall and separation or reattachment or whatever, then the curve becomes asymmetric. And if you integrate over a full cycle, you get a net moment. So that would drive the object into rotation. In that case, it appears to be showing a damping condition because it's positive rotation, and the net integral over the pitching moment would be the reverse. So that would actually be a damping case. That scenario pops up again later. Another thing which is also very scary, and it turns out to have been studied at my old university, University of Southampton, Simon Newman. They had some accidents with weight shift controlled ultralights, which is, put an engine on a hang glider and off you go. What can possibly go wrong? Well, they apparently go end over end, and that also is nose down rotation, which is awful. And you can see again in the testimony, the pitch rates that have been observed are up to 360 degrees per second. So imagine trying to hang on to that thing going end over end. Some pilots obviously didn't make it. Others that did survive, described the sequence of events, and some fairly complex analysis was done. The aeroelastic deformation of the wing, in that case, probably plays an important role. Another thing which popped up in my historical meanderings was the Douglas D558, which was sort of a Mark II type design. They didn't have ejection seats. They had a separable nose cone, and they were worried about whether that would tumble before the parachute deployed. That resembles actually some of the capsule questions that we'll address later. Quite a bit of wind tunnel testing was done, and again, models have tested in the old vertical tunnel over on the east side. They pretty much deduced then what was driving the motion, and they noted in that case that there is a possible geometry that causes spontaneous rotation in crossflow, which is properly called the Savonius rotor. That's the sort of two halves of an oil can offset to make a little primitive wind turbine. However, most of the geometries we're dealing with do not have that kind of asymmetry. It doesn't have the anti-symmetry from left to right. So that effect is not applicable in most of these cases. Many, many other studies. People have done the two-dimensional cards and the tumbling strips of paper. Very academic and nerdy thing. Rocket segments, longish cylinders will tumble in descent. So there's a range safety question. How much side force can they generate and where would they drift in trajectory wise? I learned week before last that the payloads from sounding rockets from Wallops are actually designed to tumble much of the time because that limits the aerodynamic heating. Distributes the heating load over the entire structure, so you don't need so much or no need any thermal protection. I didn't know that before. Lots of other weird and wonderful things. People are worried about re-entry of orbital debris, which would likely be tumbling end over end. So that takes us from subsonic to hypersonic, way beyond the scope of what I'm talking about today. And it gets weirder and more wonderful right down the bottom. People have actually studied injections of fuel pellets, little things that look like a Tylenol pill, into fusion reactors, and the Reynolds numbers are very low, and they worry about whether the thing will spontaneously tumble as it goes in. Who knew? So how did we get into this mess? Colleagues in Japan that have many magnetic suspension systems in their wind tunnels were working on drag of axially aligned cylinders. That's a nice academic thing to worry about. People have studied spheres for 100 years, so this is sort of one step beyond that. Large scale separation from the front lip. And they found there was a critical length to diameter ratio, a little bit greater than 1, where the separated flow would reattach to the circular center body, hence causing a dip in the drag coefficient, and so on. So we thought, well, that's interesting. If they can do it, why can't we do it? So we set up models. I actually have a cylinder here. They're about this big, length to diameter ratio of 1, magnet inside. Careful because it tracks everything. And when we tried it, it didn't behave. And this is a view from below, and at reduced frame rate, the thing starts tumbling spontaneously end over end. And our response to that at the time was, excuse my French, but basically bugger it. It means we can't measure what we wanted to measure. Right at that time, COVID hit, the lab got shut down, the student working on it then went off and completed his master's degree by doing computational analysis on the same geometry using the SC flow code. I think Hiro was advising a little bit on that. A little bit inconclusive in the results because it's a very complex problem. Everything's time dependent. You've got to impose a tumble rate and so on and so on. But then a year or so, maybe 18 months ago, my NASA lead, Mark Schonenberger, gets a call or an email from somewhere. What if we drop these capsules from a balloon and they start descending? And if they start tumbling, are they going to drift off and cause a range safety issue? Which is one of the things that's been looked at before with these booster segments. So we thought, well, we'll just dust off this and start actually making measurements. And tumbling of capsules, of course, does happen. There's this famous photos of, this is not strictly fair, but this is the Genesis capsule where the drogue parachute didn't deploy for reasons we don't need to go into. And it was doing this very complex motion before impacting. Most of the science payload actually survived that, which was kind of good. So we got serious and started a test program. So we're using the magnetic suspension dynamics tunnel, as it's so called now, which is a magnetic suspension system originally built by MIT many years ago. Low-speed wind tunnel, heavily modified. Basically, anything electronic has been changed. The electromagnet assembly and the wind tunnel still remain more or less as original. And then we began to do a family of geometries, which is going to be the bulk of the discussion. The history of that hardware, it was built at MIT. It was brought to Langley in the sort of late 1990s, lived here for about 10 years in building 1230. It was going to be thrown away. I said, no, it's too nice to throw away. I'll take it to ODU, which we did. It lived at ODU for about 10 years, was never fully recommissioned. And then it was brought back to Langley on loan to support some of this capsule dynamic stability work. And it continues to chug along. So the electromagnet assembly surrounding the test section, as originally designed, the axis of magnetization of the model was along the axis of the wind tunnel. which suited the testing they were doing at the time. I'll have a few results right at the very end from that era. We needed different configurations. So actually, if you look at the little table there, everything that turns red was changed. We basically rewired everything so that all of the field components got swapped around, and the axis of magnetization is now vertical, so transverse to the flow. And that gives us a degree of freedom where there's basically no constraint in the yaw rotation. It's like a zero friction pivot in yaw. The position of the model has to be sensed at all times because this is open loop unstable. So MIT had a still unique electromagnetic sensor that's like a multi-axis variable differential transformer. All the electronics for that have been changed at least twice over the years, and it's still working reasonably well. We've added also motion tracking cameras to better capture the trajectory of these models. In this case, since it's in continuous rotation, it's really only used to confirm that it's rotating true about one axis. There's no coning or wobbling going on. Quite a complicated feedback control system. Dave Cox, who's now retired, did most of the software. My current PhD student, Caleb Hull, has taken this on and is keeping everything going and is making enhancements. So life is still good. Bunch of power supplies. It does not draw very much power, contrary to most people's belief. It's mostly reactive power transfer from capacitors into the magnetic field and back again. The dynamics of the whole system are very complicated. So we've been doing mode analysis and so forth. The mode that worries us for today is the right-hand one's got the big circle around it, so-called compass needle mode. The axis of magnetization tries to align with a steady state vertical field that's applied, and that gives it stiffness, but no direct control or damping. So we have to watch for a coning or wobbling motion about that axis. Calibration is challenging, but we're making progress with that as well. And I think the main topic was to talk about the aerodynamic results. So we took a family of geometries. We actually started with a sphere, because why not? Everyone's tested spheres, and a spinning sphere in crossflow gives you Magnus force. So that would confirm that we could actually measure the side force with some reliability. Then there's the one-to-one cylinder. The green is a 3D printed shell. The sort of browny shaded circle in the middle is a spherical neodymium magnet magnetized in the direction of the red arrow, so along a transverse axis in that case. So that was the original geometry we wanted to test. Then we had a family of capsule-like geometries where basically a cone angle is put on the front and the back of the cylinder. And finally, of course, as in video, the Genesis capsule, which is now asymmetric front to back, that was also tested. The setup, you levitate the model, and sometimes if you turn the wind on, as with the cylinder case, the thing will spontaneously begin to tumble end over end. Sometimes you have to nudge it a little bit because most of the capsule-like geometries have static stability over at least a small range of angles of attack. So following prior tradition, an air jet was arranged on a retractable sting. So it came forward and you sort of puff some air on one side of the model to spin it up a little bit. Then you retract the sting, start up the tunnel. And in all cases, then the model locks into the flow. It kind of spins up to a steady speed, which is very closely proportional to tunnel speed, like a constant reduced frequency. The physical mechanism involved, going back to the Northrop discussion, because these models have a high degree of symmetry, if you did pitching moment versus angle over full 360-degree rotation, you'd get a symmetric, or well, I guess anti-symmetric curve. The integral over one cycle would be 0. So from static data, nothing interesting would happen. The dynamics are key. It actually has to have an angular rate, which then distorts that curve. And measuring it and predicting it is going to be the key to fully understanding what's going on. But in some way or other, the motion locks into the wake structure. So understanding the vortex shedding into the wake, or the formation and destruction of structures in the wake is key to the full understanding. We started with spheres because they've been tested before. There's a graph on the left from another reference for a strut-supported sphere spinning at different rates in different low-speed flows. And it shows the classical positive Magnus effect and also the inverse Magnus effect. That's not a recent discovery, but relatively recent, depending on the precise conditions, Reynolds numbers, and so on. The side force can correspond to the circulation-induced lift direction or the reverse, which is kind of cute. That's being exploited quite a bit now in the sport of cricket, where they make the cricket ball swing one way and then all of a sudden it'll swing the opposite way, even though it looks like it shouldn't. Very sneaky. So we tested a few spinning spheres. It's not quite a reproduction of the original data because we can't motor the thing continuously. It's always in a spin down condition, so it's an unsteady, but we thought it was sort of close enough to verify that we were measuring forces correctly. So here we are now with a 1-to-1 cylinder. So it's this model, length to diameter ratio of 1. And there are various sizes. This happens to be the largest size of the 3 plotted there. Spin rate versus tunnel speed. You can tell that once it's kind of locked in, that ratio stays pretty much the same. Those lines are pretty much straight. The dimensionless frequency then is roughly the same for all different sizes. Slight asterisk on wall interference corrections there. And then we discovered unexpectedly that there would also be a stable lock-in frequency at a much lower value. So you can see down here, the same model can spin up here or down there. That was a surprise, and I think that's a new discovery. So you've got side force coefficients and drag coefficients to the right. Drag is roughly what one would expect from a model of this geometry, 1 and a bit. This is a cylinder going end over end. Side force coefficients a little bit less than 0.2, and the low spin rate value is roughly 0. So there's some substantial difference there as well. The lock-in phenomena, is it really locked into the flow? So you can take the same data, same condition, I suppose, start the tunnel up, reach a certain spin rate, which is up in here somewhere, and then stop the tunnel. So the blue is the tunnel dynamic pressure. Red is the observed spin rate of the model. You remove the flow, it begins to just decay through natural damping, but rather slowly. It takes 30 seconds or more to come halfway down. If you then restart the tunnel, which was the dotted line, the spin frequency then picks right up again and goes back to where it was before. So it really is locked into the flow. If you wait longer before you restart the tunnel, which is a solid line, then the spin rate decays and locks into this lower value. So you can cause it to be up here or down there by the history of the flow immediately preceding that instant. This now goes on to the single parameter family. So that's the things that look like re-entry capsules, only they're symmetric front to back, which most re-entry capsules would not be, but this reduces the number of geometric variables to 1, which is just the cone angle. And you see then slightly different lock-in frequencies for different geometries, similar overall drag coefficients, slightly higher side force coefficients. This is giving you basically a lift to drag ratio that would then give you the trajectory for range safety kinds of analysis. The lift to drag ratio of what, 0.3 or something. So not so interesting. And then we went on to the Genesis capsule. Then it got even more crazy. So you'd start up at a particular tunnel speed, nudge the thing into motion, it would lock into the flow, you'd work the tunnel speed up, work it up, work it up. All of a sudden, there's kind of a shudder, and the model spontaneously spins up to a higher frequency. And then once it's up there, it doesn't want to come back. So a true hysteretic effect. It jumps up here, you can then go faster and slower and all day long go up and down that higher line. It'll never spontaneously come back down again. You have to basically stop everything, restart, and then it comes up this lower line. Again, I'd not seen that reported in the literature before. If you do drag and side force coefficients as before, obviously scattered because we've got two different behaviors here, but similar orders of magnitude. To summarize results there, so you've got the sphere, which doesn't show the tumbling behavior because of symmetry, the one-to-one cylinder, the family of geometries, and then the Genesis capsule. The dimensionless spin ratios, all in the same sort of range for the capsule-like shapes. Drag coefficients, somewhat comparable. Side force coefficients vary a little bit. The highest side force was the highest spin rate condition for the Genesis capsule. So you get about 0.3 side force compared to 1.3 in drag. So lift to drag ratio of about 1/4. We believe that the lock-in phenomena must be related to flow structures in the wake. The wavelength of the structures, if you go from the spin ratios as shown there to the physical wavelengths, it's actually quite large. So it's many, many model diameters wavelength in the wake, which I think is not quite what we expected, but that's the way the numbers come out. And loosely related work is now underway to try and get more information on what the wake structure actually is, to see whether we can figure out what's driving the lock-in phenomena. Now, there's some prior work was done on Magnus force testing with magnetic suspension systems way back. And my old university, University of Southampton, was in on it before I actually got there as a student. And MIT was in on it way back with the same system that we're still using in a highly modified form. And I've realized later that there was some sort of adversarial competition between the two, but never mind. So at Southampton, they tested spinning ogive cylinder models. You see something of the same class there in the series of photos, and you can vary the angle of attack. The spin is about the long axis of the model, so nominally the axis of the wind tunnel. This would be more like an artillery shell at angle of attack. Artillery shells, they're rifled for gyroscopic stability. When they reach the top of their arc and begin to descend, the gyroscopic effect says don't turn nose down, stay at angle of attack. So then you get a aerodynamic angle of attack, and the Magnus effect causes the shell to drift off one way or the other. So there was a lot of interest back in the day in analyzing and understanding this effect. So some data from Southampton, a good deal more from MIT, and this showed for, again, ogive cylinder shape, 5:1 length to diameter ratio. It also showed that the Magnus force, which is the left-hand plot, could be of either sign. So you see positive and negative values there, depending on the aerodynamic angle of attack in the tunnel. And the right-hand plot is basically the same condition with a dummy sting put up the back. And clearly there's a huge support interference influence there, which is one of the arguments for magnetic suspension. MIT was very good at keeping everything. I don't know why, they were just obsessed with that. And so actually one of those models still survives. It's right here and very faded now because this is 50 years old. But the stripes that they used to monitor the rotation rate from a little optical sensor off to the side of the tunnel. This is just solid steel. The models we use now have permanent magnet cores. This was just a freely magnetized iron core. But that's literally one of the originals from way back. So where are we heading with this? The magnetic suspension tunnel we regard now as being in production mode. The main emphasis is producing aerodynamic data rather than developing the system. Developments continue, but they're kind of done off to the side. So we got this database now for low-speed tumbling of capsule shapes. We're doing some related work, which would give more information on the wake structures. And one thing we'd like to do is get some flow visualization capability in the magnetic suspension tunnel, which is a problem because it's an open loop circuit in a lab. So we can't just put smoke through there or the fire alarm would go off. So we're actually looking at a water fog seeding system for PIV, which surprisingly MIT looked at way back in the day, more than 50 years ago, because they wanted to do flow visualization for a similar purpose. We now want to do quantitative measurements, so we'll see how that goes. And there's some interest now in the issue of capsules spinning about their flight direction. So that's often a rotation that's imposed to improve stability. There's particular projects underway now. So we may reorient the coils again so that we can have axial magnetization and a free axis about the direction of flight, you know, the x-axis of the tunnel rather than the transverse axis. And our Japanese colleagues have a number of these systems in play, so I'd like to see them working on similar problems. They're more of the academic mindset, so I think they will, and they have an army of students available. So acknowledgements to Langley Funding that has underwritten all this, and I'll take questions.
One hour for questions. So.
An hour?
Let's go. Let's go. Speaker back up.
Colin, back to the genesis, the film that you showed, the video.
Yep.
Probably all seen. Understanding it wasn't a pure auto rotation pitch. Have you gone back and looked at your data tunnel and done any correlation with the rates that you saw there?
We sort of had a look at that. You know, Mark Schoenberger was one of the people that tried to reconstruct from the video, but it starts at a higher Mach number than we're at. It's all transient, so as it's plunging through the atmosphere, you know, density's going up, Mach numbers changing. There's not really a clear comparison. So I guess the answer is sort of no. We looked at it, but I don't think you can compare one to one. And it was a more complex motion because it was spinning about its flight, nominal flight direction, as well as apparently going end over end. So it's more like a wobble rather than a pure tumble.
there was a mention of limitations on seating the flow, considering it's an open circuit tunnel. Has there been thought to building a return loop onto the tunnel?
We haven't thought about a return loop, to be honest. Back in its prior incarnation, it was in 1230, and they attached a large diameter flexible hose to the exit and put it out a window. So I think you can still just about see which window was taken out on one of the wings of 1230 so that the smoke would be blown outside. We are more than one wall away from the outside of the building where we are, so it's not feasible. I haven't really thought about return circuit. Probably not enough lab space and may not be worth it. So we're going to try the water fog thing, which MIT tried, and there's some hope that it would work just well enough for our purposes.
With the ultralights, those guys, what was the impulse or the dynamics that would get them into a situation?
Yeah, $100 gallows.
They say it was all triggered by basically going into stall, whether deliberately or accidentally. Some of the pilots were trying to do loop-the-loops and things, just stunt pilots showing off. And if that went wrong, things got bad in a hurry. But there were other cases where just an inexperienced pilot would stall, and then the behavior following that, depending on exact conditions and the design of the vehicle and so on, it could end up in this rather drastic tumbling motion. Does the YB49 model still exist at the spin tunnel?
Pictures of it.
Model's gone. Okay. Yeah, one of the conclusions from the reports were that the experimental tests, it either tumbled or it didn't, and that was about all they could deduce. There was no additional information available to kind of give more background. So it, you know, it was a kind of a binary thing, yes or no. So there's probably scope with more instrumentation for doing it again if there was interest. Yeah, onboard telemetry, et cetera, et cetera.
You have the original report.
I've got a couple, yeah. They're all open, yeah.
Let's take our speaker and use it. All right, thank you online.
What kind of patients are you?